To start, and over to you.
Thank you. The one thing I'm not going to do is ask any questions because it's clear this is a tough crowd. And what I'd like to talk to you about is a relatively new technology around fiber optics. I mean, we've been using fiber optics in the borehole for a while, doing temperature measurements and strain measurements and things. Now I want to tell you about a system that we actually listen to the wellbore. Now what that means, let me give you an example. If I was to lay a fiber between here and Heathrow Airport, and all of you walked to Heathrow Airport, I could follow you, each and every one of you, to the airport, position you to a meter accuracy and listen to what you're doing. What it does, what I've got is a system that I can have the equivalent of microphones every meter along a fiber, but it's just the fiber. All I listen to is the fiber, nothing else. So if there was a fiber already in the ground between here and Heathrow, equally I can listen to that fiber because there's nothing connected to it at all. And so that gives us a lot of possibilities of how to use it. It's just a box, and we connect to a standard communications fiber. There's nothing special about the fiber at all. And what I can do is, the location accuracy I can get to a meter accuracy. It's about 50 kilometers. We expect to be able to go to 100 kilometers or so, but that's more or less the idea of it. What is the sensitivity of it? It's similar to seismic. It's not quite as sensitive as a geophone, for example, or an accelerometer. But we're getting better and better by the day. Of course, apart from oil and gas, it's got lots of other interesting uses. Perimeter security, following things. I can follow trains, I can follow cars, I can follow ships going in harbors, all kinds of things. But today I'm here to speak about what we can do in wellbores and for oil fields. I think downhole we can listen to things. If I can track things moving, I can listen to flow. If I can hear individual events occurring in the borehole, then I can position things in depth. And I'll show you some of that a little later. I can detect things like sand coming into boreholes. Anything that makes a sound, I can listen to on the fiber. Here's a simple example. This is just a test of us running, first of all, a microphone, and then the fiber listening to a leak that we're artificially making in a 6-inch line at a very low pressure. So that's what you're listening to is the mic. Now you'll hear the fiber. Pretty exciting. So this is at that particular meter point, and you see there that I've got a representation of the leak and then the closing of the hammer. So that gives an indication of how sensitive the system is in terms of and the fidelity of the system to be able to listen to a real sound. Now, if I just take that a little further, what I'm doing is building a story here. So excuse me, I'm not yet onto boreholes and things, but this is all about now. Being able to track a moving object. So as somebody walks along a field, you don't hear anything on a microphone. But if I listen to my fiber, which is buried about 30 centimeters below the ground, I can listen to him moving past a certain point in the fiber, which is that meter point there. Now, if I listen to another point here, then I can position the energy of that point over the two places. Now what you'll see here is that you've got here's distance and here's time. Therefore, his movement across that field is the velocity. So I'm tracking the velocity of his movement. So I'm tracking somebody, and I'm also able to track the velocity of that movement. So if I go into a little bit of case histories here. What this is a tight gas well, and you can see here we were able to push the fiber down into the well, down to this point in the well. We weren't able, unfortunately, to get the entire
portion of the well. This is the temperature log in the well bore, which doesn't really show very much. It was very. We still don't know why. The same system was used in a well next door afterwards, and the temperature measurement was a lot better. We're not sure why it's this, but it really doesn't tell you anything about this. And as you can see, there are 9 zones in this well, all of which were fractured. And as I say, we only got to this point here. The client thought that the entire section was pretty homogeneous, and therefore his production would be coming from all 9 fractured zones. So when we started listening to the well, and this is 5 times normal speed, but this is real-time data. This is what you get at the well site. And as you can see here, we got 3 areas of noise. One here in zone 7, one here in zone 9, and we've got this, which is outside the zones of production, but it is to do with vibration in the bend. Okay, so within certainly the 5 zones we were monitoring, you can see there that we can see that there's sound coming into that well at two particular zones. So at this point, it looks like we can say, well, the 2 of the zones are producing something, or something's going on at these 2 zones. The other zones are quiet. So if I then go to, and that's the well in the production phase, that's the well producing. If I now go to the well as we shut the well in, what you'll see here, so the well's just been shut in, and what you'll see immediately is something falling down the well. Remember, if it's at an angle going up, because this is distance and this is time, if it's going that way, it's something rising up the well. If the curve is going this way, it's coming down the well. So what we're seeing there, as soon as the well shut in, we see falling of here, and this is falling water. And you'll notice the falling water goes back into this zone. Okay, so you can see here also the quietening down of zone 7 as the production is stopped. But throughout here, you'll see different angles here. You'll see things continuing to fall, but you also see some gas still escaping up through the well. This is as the well is brought on production again. And you'll see here nothing much happens for the start, the first 15 minutes. And then what you start to see is a trend, a low velocity trend up the well. You'll see this trending angle here. And then you also see a much faster flow there. Okay, so you've got a slow flow here and a much faster flow there. So what we've got here is water coming out of this zone again, and the water that's sitting in the sump there is drawn up the well, and then the faster gas is taken over the top. Okay, so we're starting to see this come on. You'll notice that this has taken a while to come back, zone 7 to come back. Now, if I look about, this is about 30 minutes after the production was started again. And you'll start to see that here's the gas coming back. And you're starting to see slugging out of there. You start to see the little peaks there coming out from that zone. And that's gas starting to come into the well and zoom along the well bore. And here, you'll see here, and this is some gas coming in here that is mixing with the water that we think is coming from the same zone, but also is still in the sump. So from a well that the oil company thought was going to produce all the way along the well bore, we've taken this well to actually only producing from this one little area here in zone 7, and potentially a small amount in zone 9. And this is just by listening to the well. This is a SAG-D well. And what you have here, here's the temperature log of the well, okay? And this is over 48 hours. You can see the surface temperature is changing, going up and down during the day and night. But you can see the temperature in the wellbore hardly changes at all. But you can see things in there. You can see the trace warming where the fluid is coming into a well. You know, fluid comes into a well, expands and heats. Gas comes into a well, expands and cools. You can see on the this is the time and horizontal distance here on our acoustic fiber, and we start to see things. We can start to see there's vibration in the kickoff point, there's vibration in the bend. We can see the pump, which I'll show you a little bit more later. But more importantly, what we can see here is the primary production zone. We can actually see the noise of the fluid coming into the well. But not only that, is we see a secondary production zone. You can see two distinct legs there. But also, as we see, remember this is over time, we start to see the oil move out of zone and along the well. So if I show you now the actual video, and this could take longer than I've got to speak, so I'll show you a little bit about it. But what you've got, this is real time. This is the data from the well site itself. And so what you've seen here, you've seen this oil that's creeping out here, okay? And then what you'll see here is you'll start to see the oil come out again as the pump spins up. You'll see there, you see the oil starting to come out there. And of course, because this is time and this is distance, the angle of that curve is the velocity of the flow of the fluid coming into and along the well. And I could show you that as it comes out. What I'll do is I'll go forward and show you the results. I'm not sure how well you can see that out there, but what we're seeing is that this is over time, remember here. I've spun this around, so depth is on the vertical and time's on the horizontal. So now what we're seeing is here's the well over time, and this is about, if I recall, it's about 70 minutes or so. So what we've got is we've got 3 cycles of the pump pulling oil into the well and along the borehole. We can tell the velocity of the flow because we can determine the angle of that curve. Depending on how we filter the data, you'll see that we can see the action in the pump. There's the pump there. But curiously enough, another way that we determine that this is the flow coming in, you'll see the vibration in the bend there. And what we're seeing is that this one, for example, this cycle is coming up, coming through the pump, and then causing that vibration in the bend as it comes around the bend and up the well. As we change to a higher frequency, you start to see some more attributes here behind it. And you can start, and of course, the more vertical the angle of the curve, the faster the movement. And so here we see some very slow moving events behind this. And you could argue that this production, because of the cyclical nature of the pump, never actually reaches the well. This was a working well. We disconnected to a fiber that was already in the well to study temperature. So we disconnected to that particular fiber. So what all of a sudden you have the ability to see wells in real time. You have the ability to see movement, which has never been seen, as far as I know, by any other technology. Here's one. This is about sand production. The client had an issue where he had sand coming into the well, but he didn't know where within the screens it was coming in. Now, let's say this is run on a different kind of fiber. Predominantly, there's 2 kinds of fiber. There's multi-mode fiber and there's single-mode fiber. We prefer single-mode fiber. So here, this is going 5 times normal speed. But all of a sudden, what they did was they started to open the choke. Here's the top and the bottom of the screen. And you can start to see, as they open the choke to open up the production, we can see exactly where the sand is coming into that well. So basically, you can go back in there and if you want to, you can work over that well and increase the production without any threat of sand from anywhere else in the production zone. This is an interesting one. I'm sure you won't see this. This is actually a well. One of the questions I'm sure you're going to ask is, how do you get a fiber into an oil well? Well, there's many ways to do that. Some of this work has been done on a wire line with fiber inside it. Some of it's been done inside coiled tubing. Some of it's been done in a hard carbon rod, the Zeeble zip-log system. This one was done on a fiber that was installed in a 1/4-inch control line, but it was done outside the casing. So during the positioning of the casing, the fiber was installed at that time. So it's the best way to install it because you're outside and you get a very quiet environment. This is so quiet that you may not see this, but this is a well at rest. And what you're seeing here is this is the bottom of casing here. There was an uncemented casing above this and then cemented casing below. And we can see leaks of fluid coming into the well. And some of them are moving slowly. I don't know if you see that. There's something moving at quite a low velocity because the curve is quite flat, and then something moving at a faster velocity there. So we're actually showing them immediately there's a leak in their casing system. But that wasn't what this was about. What this was about was they were doing some pressure testing outside the well bore. So they were firing guns into the formation, but not breaking the seal on the casing. So they were trying to get pressure readings within each strata. So what you see here, this is interesting. Remember the fibers outside the casing. Here in this first slide, what you're seeing here is the noise of the casing expansion. Remember, there's no cementing here, so the casing is allowed to expand. So as they pressure up to fire the guns, we can see the noise that creates and the stress that's put on the casing. Here, there's a gun firing here, and you can see the reverberations of that going up into the uncemented casing there. This is still pressure causing expansion of the casing, and here is the reverberation of the gun. Now, if I look at a sequence of guns, in actual fact, these guns are fired by pressure. There's a membrane in the casing, so that actually fires a piston and fires the gun and doesn't break the seal. So the plan here was actually to fire these sequentially from the bottom to the top. There were 20 guns. And as you can see, they fired all over the place. But curiously, what we find interesting, and I don't have the answer to this, maybe some of you gentlemen do. But here was the entire sequence. And what you see here is we have all the guns firing, and we determine all the guns that are firing over the sequence. And here's a gun firing, here's a gun firing, there's a gun firing, there's a gun firing. But isn't it interesting to see that some of these have noise associated with them, and some of these lasted 45 minutes after the event. So something was moving in those strata for up to 45 minutes after the event, whereas some of them were very quiet and immediately quiet. So what does that mean? If unfortunately we didn't have the opportunity to go back and see, well, how did that relate to production, or how did that relate to any other further program of fracturing, etc., because this was just a test well. So unfortunately we didn't see that, but I think you'll see that here is a technology that allows you to do an awful lot more with a well bore. It allows you to determine the entry points of fluid and gas. You can listen to different things going on in the well. You can listen to mechanical movement. You can listen to leaks. You can listen to fracturing. You can listen to microseismics. There's an awful lot of different things you can do with this technology. It's in its early days, and we hope to be able to come back soon with an awful lot more case histories to show you. But we've recently done some frac monitoring with this system, and being able to tell an awful lot of things. For example, I'm not allowed to show you that data yet, maybe next time, but it certainly shows you where the fluid is going into the rock the individual zones that are taking fluid and then producing fluid. So, a little safe sales pitch at the end, I suppose. But the great thing is that the fiber is just simple fiber. It's virtually, it costs nothing. What it costs is the cost of installing this into the well. That's the cost that you'll come up against. It's perfect for hazardous conditions. There's no electronics. It's just a piece of glass. And so it's very good to put in refineries or pipelines or difficult areas where you're concerned about things. And that's what I had to say. So thank you very much for listening, and happy to take questions.
Just step to one side so I can use these microphones, and you have one anyway.
Okay.
Okay, just a question, you may have addressed it, but Fotech is how old as a company?
Fotech started in June the 20th, 2008.
Okay, and the technology comes out of the defense industry?
No, the technology actually came from, originally developed by Professor Rogers at Imperial College and later Surrey University. They started a spin-out company, which we bought and further developed the technology.
Okay. And private equity backed at the moment? Private equity backed. It's
Scottish Equity Partners and Energy Ventures are the backers of the technology.
Okay. And what sort of, I mean, we talked about this in a different context about what sort of reception are you getting from the big players? Are they like Schlumberger, for example? Are they interested in this?
I
don't like this? Well, I mean, what do they have to say?
I think the general opinion is a bit bemusement at the moment. I think it's nobody can quite believe what it can do, and I think part of the issue of acceptance is to do with the ability to get this fiber into the wells. I think the cost of the service, the cost of the technology is nothing really when compared to the price of an oil well. But of course, the installation of it requires a certain amount of money and a certain amount of commitment and belief in the technology. And I think inevitably it's going to take time for that belief to come, because it's something that's never been seen before in terms of a technology. So any oil companies out there, please give us a try.
Okay, anybody got any questions? Two here. Yeah.
Oh no.
Sorry.
Your reputation goes in front of you. So.
Can you hear?
Yes.
Yeah.
Okay. I noticed you're talking all the time about sound.
Yes.
Then many of your graphs were showing temperature. What was the conversion? Is that real? I mean, how did you come about measuring temperature with the fiber optics?
There's a way to measure temperature over fiber optics, which has been going on for many years now. Well, many years, 15 years or so, they've been measuring over fiber. That can be done on the same fiber, or it can be done on a different fiber. The temperature you saw there were readings that were taken either simultaneously with the acoustic information, or after the fact. If there was only one fiber there, we'd record temperature and then we'd record acoustics.
I noticed that you have a fiber, but you didn't. There is a decoder at one end,
yes.
I assume.
Yes.
But there is something, a sensor at the front, the opening of the fiber. You haven't really talked about anything. You just say, put the fiber in the well, take measurement.
Yes.
Can you explain it a little bit better? So
the only electronics are the electronics that would be on the surface. Everything else is just the fiber. So there's nothing on the end of the fiber that we use, or anything on the fiber at any point. It's just a pure fiber.
But the fiber has a micro hole, right, to receive something?
No, it's standard communications fiber. I could listen to this building if I wanted to, and listen to what was going on inside the building. It's all about how, as we shine light down a fiber, as we pulse a fiber, and if I make any sound near that fiber,
it creates a strain on that fiber which slightly microscopically elongates the fiber. And therefore, as I send light down that fiber, it changes the phase of the light. And I extract acoustic information from the phase change.
We had a, yeah.
He's just answered my question.
Oh, okay. Okay. Anybody else? Yeah.
My hypothesis for the sustained noise after the fracking in some of those wells would be that there'll be some kind of crystalline fracturing that was taking place through the reservoir as a combination of the initial hit from the gun and the oil or gas pressure. That would be my suggestion.
Would that be helpful to you in your interpretation of that zone?
Not particularly, but it just occurs to me as a... Well, it probably would actually, because I would think that would, if that were the case, it would give information as to the nature of the fracturing process deep within the reservoir, which is not otherwise visible.
Right, okay. Yeah, it was something that we thought was interesting, but we didn't know how valuable it is. Certainly not as valuable as being able to follow the flow as we saw in the SAGD or the tight gas examples.
Just on that point, I guess as an industry...
Hang on, just like the fact that you need to have your words preserved for posterity.
As an industry, we struggle to understand where the frac fluid actually goes, and then we don't get as much of the frac fluid back as we put in. So being able to understand that will definitely help.
Yes, I think so, and I think the recent work that has been done with this technology it's a start now. I think now that we've been given the opportunity to get into some of these wells that are being fracked, I think you'll start to see an awful lot of wells taking up this technology now. At least we hope so.
I guess those wells that struggle on the economics often anyway, so that's the challenge you said you're facing, that getting into those sort of marginal economic wells with an extra cost added on, I guess, is the challenge.
Yeah, I suppose one thing that I think is that if you look at the number of zones that actually end up producing in a well, you might well be able to frack less in some areas, which also saves a huge amount of money. The cost of fracking is tremendously high, and more so in various geographies around the world. So if we can create a balance of being able to tell them, what's worth producing and what's not, then...
Yeah, we're working on, I work on National Grid, and we're working on carbon capture and storage. So I'm trying to find out how applicable your technology will be in tracking carbon dioxide movement in a well.
Yeah, we've done some work on injection wells as well, and we've been able to see exactly where the zones are taking gas or steam. We've also done them with steam, so we can actually track the entry points.
Okay, so we're limited to a region just at the bottom, around the bottom hole of the well?
No, you can do the whole well. Actually, you can do the well and all the way through the plumbing as well, if you like, because we can do 50 kilometers. So I can, in essence, I can do several wells with one fiber, if you like, but it's a little complicated. But certainly you can do up a well and along a pipeline, for example. So.
Also, I noticed in your charts that you could track gas and liquid movements. So I was wondering, how do you detect the difference between gas and liquid in the wells, and can your technology detect phase changes from liquid to gas?
I know where you're going here is three-phase flow measurement. and it's an early technology. We think that down the road there's a possibility that we'll be able to do that, but it's still early to be able to do that. In terms of the difference in oil and gas, it's certainly by spectral analysis, which we also do real time at the well site. We can determine the velocity of the flow coming out of any zone, and therefore determine whether it's more likely to be oil and gas. There's quite a significant difference in those profiles, so we can certainly differentiate between the two.
Okay, one more.
Hi.
I think one more, and then we
Hi.
perhaps need to move on. Yeah, please.
Can you differentiate between noise and an acoustic event?
If there's a difference in the spectral content of that frequency, then yes, absolutely, yeah. It depends. I mean, if gas is coming in at 3.5 kilohertz and there's a machine that's going at 3.5 kilohertz at exactly the same point, then I'd have a tough time being able to do it. But if it's just a few meters away, then I can, because remember, what I'm doing is looking at every point in the fiber at a meter accuracy. So I can differentiate between two points very close together.
There's another question is that because of the hydrogen, there is a hydrogen darkening. I mean, how your fiber is affected with hydrogen darkening?
I think essentially it's the same as all other fibers. I mean, our fiber isn't any different because we don't use any particular kind of fiber. We use any kind of fiber. But I think you'll find that over the last 10 years there's been a huge improvement in the ability to work either around dark fibers or to put inhibitors so the fiber doesn't darken. The other thing is that single mode fiber is more homogeneous than multi-mode fiber and is less susceptible to darkening because of the way it's constructed. And now temperature measurements are moving towards, some temperature measurements are moving towards single mode fiber for that reason, especially in high temperature areas where darkening seems to be more the issue.
I'm wondering if you've tried installing any of this in a pipeline.
Yes, we have. We're installing a major project at the moment on pipelines, and we're doing leak detection along that pipeline, and down to very low flow rates at very low pressures. So yes, we're already doing that, and you can do that either with. Sometimes there's communications fiber already in the ground, close to a pipeline that we can use. We can listen to that. Other times, we'd have to just strap on a fiber to the pipeline, or bury it very shallow next to a pipeline, for example.
Okay, let's thank you. I mean, Doug and his colleague are obviously going to be around when we have coffee, so I'm sure there are more questions. So thanks for that. We didn't escape from seismic and geophysics quite as much as I thought.
Well, it looks like seismic, doesn't it?
It does. And can I buy some shares in your company? I think is my other question. Thank you, Doug. Thanks very much.
Thank you very much. Thank you. Thank you very much.
We're going to start off with Maggie Thompson from RPS, who's going to talk about how you select and how you screen EOR technologies for application. So, Maggie, over to you.